Okay, this is the third section from chapter 14, dealing with kinetics. And as we've learned up until now, we've learned a couple of things. We learned in our first section a little bit about when you know the rate of one reactant or product, its disappearance or appearance, you can use the coefficients from the balanced equation. Remember where you have 2a plus b makes 3c. You could say that 1/2, because that 2 comes down here, 1/2 the rate of A equals 1 over 1. So the rate of B, which is equal to 1/3 the rate of C. So that was in our first section. Then in our last section, we learned about rate laws, where the rate is equal to K times the concentration of A raised to some power times the concentration of B raised to some power, possibly C, possibly D, you never know. So hopefully we're familiar with that. Now, this section deals with the time aspect. Anytime that they ask you a question on the AP exam that relates to how long does it take, how much time has passed since this has happened, you're going to be using what are called the integrated rate laws. They are given on the AP exam, and we'll see them here in just a minute. So we're going to be familiar with and be able to use the first and second order rate equations. We're going to be able to determine whether a reaction is first or second order by graphing it. And we're going to be able to use half-lives for first and second order reactions. So like I said in the first section of this chapter, we learned that the rate of a first order reaction can be found by taking the change in the concentration of A over time. Then in the second section, we used rate laws to find instantaneous rate. So remember, this here would have been considered the average rate, where this one here would be called the instantaneous rate at any given point. Now, when we use, and we actually don't have to do this, but if you use integration from calculus, the relationship in the second equation can be transformed into an equation that relates the concentration of A at the start of the reaction to any time during that reaction. And the equation looks like that. Again, don't ask, it doesn't matter how we came across that. What's important is that is the equation. So this is what is called the integrated rate law for a first order reaction. So this equation you can only use when it is a first order reaction. If it's second order or third order, you cannot use it. So here are a couple things. Ln, that stands for the natural log. That is a button on your calculator. This is the concentration of A at whatever time they mention. So they might say 30 seconds into the reaction, blah, 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 blah. So again, here's natural log again. Here is the concentration of A at time 0. This is the rate law constant, just like how we saw when we had rate equals K times A. That's that same K right there, and that is whatever time they mention in there. So like I said, that equation is given on the AP exam, and again, they don't tell you anything about it, but it has to be for a first order reaction. Okay, if we arrange that a little bit and move things around a little bit, we can see that we can get the y equals mx plus b format, where this is y, this is mx, and this would be b. And if we remember correctly, that m is the slope of the graph. So if we're asked about the slope of a graph, the slope is equal to negative k, where that right there is the m. And then obviously b is the y-intercept, so that would be your y-intercept is the natural log of a at time 0. Now, what can we use these equations for? We can use them to determine the concentration of a reactant remaining at any time after the reaction has started. So again, notice the time factor. We can use it to find how much time is required for a reaction, for a sample to react. And we can also use the time required for a reactant concentration to fall to a certain level. So again, notice in all of these is they're all dealing with time. An important thing to remember is that usually we do use molarity when we're talking about concentration, but if we're using gases, a lot of times it can be density, it could be pressure, things like that. So let's look at an example of this. It says the first order rate constant for the decomposition of a certain insecticide in water is 1.45 years to the minus 1. Okay, so that's the first order rate constant. So we know that K is equal to 1.45 years to the minus 1. And it says a quantity of this insecticide is washed into a lake on June 1st, leading to a concentration of 5 times 10 to the negative 7th grams per cubic centimeter or grams per milliliter of water. So that is our initial concentration. So the concentration of A at time 0 would be 5.0 times 10 to the negative 7th grams per cubic centimeter. Assume that the average temperature of the lake is 12 degrees Celsius. They want to know what is the concentration of the insecticide on June 1st of the following year. So we know that our time is going to equal 1 year, and they want to know what's the concentration of that at that time, which again, we could, instead of T, we could write 1 year. So again, you know your variables, you put these numbers into the equation, and then you basically solve. So when we solve for the natural log of A at 1 year, we've got negative K times T plus the natural log of the initial concentration of A. So the way that this equation is written, it was written in that natural, or in the y equals mx plus b format, where we were solving for y. Now, once you solve this part, so you're going to put this in your calculator, and again, this is something that I would practice with, is in my calculator, I would do this part first, and then I would hit plus, and then hit natural log, and then put this part in parentheses, and then you would get this, you should get this answer of negative 15.96. But again, we don't want the natural log of the concentration of A, we want just the concentration of A. So when you do that, you have to take the opposite of natural log, which is the e to the x button. It's not the double E, it's not the exp button. It should be right above your natural log button, and it looks like an E with an X. So if we take that to both sides, basically if you take e to the natural log of something, they cancel each other out. So we just have the concentration of A at 1 year is going to be e to the negative 15.96. And again, I would do this yourself on your calculator. You should get an answer of 1.2 times 10 to the negative 7th. So it started out at 5 times 10 to the negative 7th, and it went down to 1.2 times 10 to the negative 7th. Okay, now part B, let's go back there real quickly. Part B says how long, so this time they just want to know the time. How long will it take for the concentration of the insecticide to drop to a certain amount, 3 times 10 to the negative 7th. So again, figure out the variables that you know, and then again just plug those numbers in and get your unknown. So we're going to rearrange the equation to solve for T. So if we look here, here is our time factor. So we subtracted that back over to this side. So here we have that. And then to get rid of the K value, we have to divide by negative K. So we're going to divide by that. Here's the negative part of that. Here's your K value. So again, we're just putting numbers into the equation, solving it. Again, try this yourself and make sure you can do this on a calculator. So we're going to take the natural log of 3 times 10 to the negative 7th minus the natural log of 5 times 10 to the negative 7th. We're going to take the negative of that number, and then we're going to divide by 1.45. And when we do that, you should get an answer of around 0.35. And again, the only units we have here are years. Now, when we do this, when we're using a first order equation, again, notice that we have that general equation of y equals mx plus b, where we've got y, mx, and b. So a good way to verify if a reaction is first order is to see if the natural log of A forms a straight line in a graph with a slope of negative k and a y-intercept of natural log of A at time 0. So I'll show you that here in just a second. So if we look at this reaction here, that's CH3NC becoming CH3CN. If we take a look at the change in the pressure over time, that pressure goes down. But if you take the natural log of the pressure, notice that if you take the natural log of all of these numbers, notice that it forms a straight line. So an easy way to determine if something is first order or not is if the natural log of the concentration, or in this case the pressure, forms a straight line. That tells you that it has to be a first order reaction. So many times they might not tell you what the reaction is in terms of first order, second order, third order, but they will give you a graph, and you have to be able to look at that graph and go, okay, the natural log is straight, so therefore it has to be first order. And we'll see what a second order one looks like here in just a second. So everything we've talked about up until now has been about first order reactions. Now we're on to the second order reaction, so we call it the second integrated rate law. So you can have a second order reaction where you can have one reactant whose concentration is raised to the second power. So you could have the rate equals K times A squared. That would be a second order reaction. Or you could have rate equals K times A to the first power and B to the first power. Those are both second order reactions. So if we look at this equation here, notice that you've got again A to the products. This is the second order reaction. So we're assuming that it's this one right here, that the rate equals K times A squared. Okay, again, this is also given on the AP exam. It also has a formula of y equals mx plus b. If we come back here real quick, if we move this over to this side, we would have 1 over a at time t equals kt plus 1 over a at time 0. So our y value on our first one, remember, was the natural log of a at time t. And if that made a straight line, then we knew it was first order. In this case, our value for y is 1 over the concentration of a at time t. And so how do you differentiate between one or the other? In a first order reaction, the natural log of a at time t, that one forms a straight line. Whereas if it's a second order reaction, the plot of 1 over a at time t forms a straight line. So here's a reaction here where they give you the time, they give you the concentration of NO2, and they ask you to determine whether it's first order or second order. And the only way you can do that is by determining which one forms a straight line. And so here we can see the first one with the natural log of NO2, it's still curved, whereas here 1 over the concentration of NO2 forms a straight line. Okay, if this one were straight, then it would be first order. Since this one is straight, we know it has to be a second order reaction. Okay, and then our final part here deals with half-life. Half-life is the amount of time required for the concentration of a reactant to drop to 1/2 of its initial value. So if you have, let's say 25 grams of something, after one half-life, let's say it has a half-life of 5 years. So here, time is equal to 0. After 5 years, you would have 12.5 grams of it. So you would say that 1 half-life has occurred. And then after 10 years, you're going to lose another half, so you'd be down to 6.25. And then after another half-life, you'd be down, so it'd be 15 years, you'd be down to, what, 3.125, and so forth. So it's the amount of time it takes for half of the reactant to drop in value. So obviously, if a reaction goes quickly, it'll have a short half-life. but they're great ways to describe how fast a reaction occurs. This information is not given on the AP exam, but it is something that you should be familiar with. There is a way to determine it mathematically, and you always get the same thing. But for a first order reaction, to find the half-life for a first order reaction, you simply take the number 0.693, and that always is the same. That doesn't change. And you simply divide it by the rate law constant. And if you'd like in class, I can show you how you get that equation without having to worry about, do you have to memorize or not. There is a way. It's kind of like how they have PV equals nRT, and then they have little m equals little m over big M on the exam, and they say, well, you should be able to find density and you should be able to find molar mass. Density equals PM over RT. Molar mass is dRT over P. For me, it's just easier to remember that instead of trying to use that equation to derive these every time. It's kind of the same sort of thing where it's pretty simple to derive it, but it's almost just as easy just to remember that for a first order reaction, the half-life is found by taking 0.693 over K. Okay, so in a first order reaction, the half-life only depends on K. So the concentration of the reactant decreases by half for each half-life, just like how we just talked about up here. Okay, for a second order reaction, the half-life does depend on reactant concentration and therefore changes as the reaction progresses. The formula for half-life for a second order reaction, somewhat similar. Notice it's not 0.693 on top though, it's 1 over, again, the rate constant, and then the concentration of A, we should call it the initial concentration of whatever your reactant is. Again, just two simple formulas that it's just easier probably just to memorize those. Okay, so we were going to look over the first and second order integrated rate equations, which we did. Again, they're both given on the AP exam. We're going to be able to determine whether a reaction is first or second order by which one's a straight line, and then we just talked about the half-lives. So if you would take a look at these, ones here in the packet. I know there's one of them, I think it's 4 or 5, that where all they do is give you graphs, and you have to determine everything based on the graphing information. And that's all.